In this lesson, we will review all of the topics from Chapter 7. I'm going to set up most of the integrals and leave the details of evaluating them to you. If you would like to see the steps written out, you can reference them in the filled out notes on the course website. The first topic in this unit was how to find areas between curves. So suppose we first of all have two curves, y equals f of x and y equals g of x. We want to find the area between them, between some value x equals a to x equals b. Now, provided that f of x is greater than g of x between a and b, we simply compute the integral from a to b of f of x minus g of x dx. If it is the case that f of x is greater than g of x sometimes, so suppose this is f and this is g, and that point in the middle is c, and we have an a value there and a b value there, you will have to produce two integrals. Your area will be given as an integral from a to c, on which we find the antiderivative of f of x minus g of x, plus the integral from c to b, where we do g of x minus f of x. Find the area between y equals x and y equals x cubed. So y equals x is a straight line. Y equals x cubed looks like this. Now the area between the curves we're looking at is this part and that part. The total area can be found either in two pieces, the first piece being an integral from -1 to 0, so that is this part over here, and there we will do x cubed minus x, because technically speaking x cubed is greater than x on that portion, dx, plus the integral from 0 to 1 of x minus x cubed. Although that's the long way, it is far simpler to just do twice the second integral because of symmetry. And if you want, you should work that out, try to differentiate, evaluate. You should get 1/2. Now next we have some sideways curves. X equals 1 minus y squared. So a standard y squared parabola looks like this. So the negative will reflect that over the y-axis and then shift it to the right 1. So there is 1 minus y squared. Now y squared minus 1 is this standard shape shifted to the left 1. And those curves intersect at y equals -1 and y equals +1. Now the area is given as an integral from -1 to 1. The upper curve is the red curve, so 1 minus y squared, minus the lower curve is y squared minus 1 dy. And let's use some symmetry, because this area is the same as that area. I can find twice the integral from 0 to 1. And combined like terms, we'll have 2 minus 2y squared dy, at which point in time you could factor out a 2 and make that 4 times the integral from 0 to 1, 1 minus y squared dy. And when you work that all out, you should get 8/3. So feel free to check that and make sure that I can actually do arithmetic. Now next, suppose we have the region enclosed by y equals sine x, y equals negative cosine x equals 0, and x equals pi. So first of all, sine x, one oscillation of sine looks like this. So this over here is 2 pi, right there we have pi. Negative cosine will begin at -1. At pi halves, we're back at 0. By pi, we're at 1. down through 0, and then down back at -1 by 2 pi. The area that we care about is this part and that part. And the intersection point happens after pi halves. That's actually 3 pi over 4. Okay, so my total area will be given as an integral from 0 to 3 pi over 4. Now on that interval, sine is greater than negative cosine, so we will have sine of x minus negative cosine of x dx, and then plus an integral from 3 pi quarters to pi, and from there we'll have negative cosine of x minus sine x dx. And you can simplify that double negative and make this into an integral from 0 to 3 pi over 4 sine x plus cosine x dx plus the integral from 3 pi over 4 to pi of negative cosine x minus sine x. Technically you could factor that negative out if you want to, just be careful. Now, when you work this all out, you should get 2 roots of 2. All of the details are worked out on my filled-in notes, so if you want to check them there, go ahead and do so. Alright, the next topic we discussed was volumes, and we had 2 methods to compute volumes. The first method was the disk method. And when you use the disk method, the important thing to remember is that you slice perpendicular to your axis of rotation. So you need to find the general slice, the area of a general slice, AX or AY, and sum over all of our slices. Find the volume obtained by rotating the region bounded by y equals e to the x, y equals 0, x equals 0, and x equals 2 about the x-axis. So y equals e to the x go through the point 0, 1, and that's exponential growth, something like this. Y equals 0 is the x-axis. X equals 0 is the y-axis, x equals 2 is over here, and that is the region we're rotating about the x-axis. Since we're rotating, our cross-sections are taken perpendicular to that axis, and they are going to be circles. The area of a cross-section is a function of x, and it's pi r squared, where in this case r is equal to e to the x. So the area of my cross-section is pi times e to the x squared. What you have to remember there is that those exponents multiply, so we have pi e to the 2x. To find the volume, you add up all the slices, which is an integral. So we integrate from x equals 0 to x equals 2, pi e to the 2x dx. This one's pretty easy, so let's work it out. When you antidifferentiate e to the 2x, you end up with 1/2, so pi over 2, e to the 2x, evaluated from 0 to 2. So that's pi over 2 times e to the 4th minus e to the 0. E to the 0 is 1, so pi halves times e to the 4th minus 1. Sometimes our cross-sections were circles with a hole inside of them, another circle. So here's an example of that. Find the volume obtained by rotating the region bounded by y equals 6 minus 2x minus x squared, and y equals x plus 6 about the line y equals 3. So y equals 6 minus 2x minus x squared. That parabola has a vertex at x equals negative b over 2a, which is negative 2 over 2 times negative 1, which ends up being at x equals negative 1. That'll help you graph your parabola. So you know that when x is 0, y is 6. When x is negative 1, if you input that into your parabola, you will get that the y value is 7. And that's your axis of symmetry to reflect. When you input 1 or negative 2, we end up with 6 minus 2 minus 1, which is 3. So roughly speaking, that's your parabola. y equals x plus 6. Starts at 6, has slope 1. It's going to end up intersecting right there. You can verify that algebraically, but these two curves intersect at x equals -3 and x equals 0. Now the area of my cross-section, I'm going to slice perpendicular to my axis of rotation. My axis of rotation is the line y equals 3. So my cross-section will be circles with holes in them. So the area of a cross-section will be pi r out squared minus pi r in squared. Now in this case, r out is the distance from your axis of rotation to your outer curve. So we're looking for the distance from there to there. Now the distance from the x-axis to the curve is given by this. So we will have that minus 3. So my r out will be 3 minus 2x minus x squared. Similarly, r in is the distance from the axis of rotation to the inner curve, and that will be x plus 6 minus 3, or x plus 3. Then the volume is given as pi times the integral from -3 to 0, r out squared, so 3 minus 2x minus x squared squared, minus x plus 3 squared. This is really tedious to work out, so don't waste your time, but you should get 108 pi over 5. Next, let's consider rotation about a vertical line. So we're going to rotate the region bounded by y equals x squared, x equals y squared, about the line x equals -1. So y equals x squared is a regular parabola, x equals y squared is a sideways parabola. We are rotating about the line x equals -1. So my slices are perpendicular to that axis of rotation, which means I will need these both in terms of y, so x equals something. So this equation is already good to go. This one will be x equals root y. Now once again, my slices will be a circle with a circular hole inside of it, so I need to find the outer radius and inner radius. So r out is the distance from my axis of rotation to the outer curve. Now that outer curve is this x equals root y. The distance from the axis of rotation to the y-axis is 1. From the y-axis to that curve is root y. So my r out is 1 plus root y. And similarly, r in will be 1 plus y squared. Now the volume is given by pi times the integral from 0 to 1. Now a technical thing to note here is that these are y values, not x values. It's because your integral is in terms of y. Your sums begin at y equals 0, end at y equals 1. It just happens to be the case that this point is 0, 0, this point is 1, 1. So the x and y coordinates match. So pi r out squared, so my outer radius is 1 plus root y squared minus r in, 1 plus y squared squared dy. The details are worked out in the notes online, but you should end up getting 29 pi over 30. As our final example, let's consider a solid with a circular base where the plane cross-sections are no longer circles. In this case, they are equilateral triangles. So the formula for the area of an equilateral triangle is root 3 over 4 times the length of a side squared. Personally, I will not make you memorize that. I would give that to you, but just for an example. So we have a circle of radius 5. and when we slice perpendicular to the x-axis, we get equilateral triangles. So if I can find the length of this, that is the length of my side. So a circle of radius 5 has the equation x squared plus y squared equals 25. Solving that for y, I get y equals plus or minus the square root of 25 minus x squared. So technically speaking, this is root 25 minus x squared. My side is twice that, so for s I use 2 roots of 25 minus x squared. Just think of this as a loaf of bread with a circular base. When you cut your slices, you get squares, but the bottom of the loaf of bread is a circle. The squares are biggest in the middle and they're smallest on the ends. So now, the volume is found by adding up all the slices. The slices begin here at -5, and they end over here at 5. So I have an integral from -5 to 5. The area of each slice is root 3 over 4 times the side squared, which is 2 root 25 minus x squared, quantity squared, times the thickness, which is dx. Now when you square this 2, you get a 4, which cancels with the 4 in the denominator. So we have root 3 integral -5 to 5 of 25 minus x squared dx. And the last thing I'd like to say is that since 25 minus x squared is an even function, you can instead compute twice the integral from 0 to 5, which is significantly easier in terms of the arithmetic. And when you work that out, you end up getting 500 root 3 over 3. But the point is, cross sections are not always circles. There will not always be a pi in your answers. So the next method was the shell method. Now, when we use the shell method, we slice parallel to the axis of rotation. So we have some kind of funky thing like this, and I'm rotating that about the y-axis, say, and I spin this little slice about the y-axis, and that produces a hollow cylinder, or in other words, a cylindrical shell. And the way to think about this was to find the circumference of the shell, so 2 pi, in this case that was x, times the height, which is f of x, times the thickness, which is dx, and integrate from a to b. That changes a little bit if your axis of rotation is not the y-axis, and this can change into f of x minus g of x if you have the region bounded by 2 curves, but in general that's the idea. Thinking of the circumference, height, and thickness I find to be quite helpful. So suppose we have this region, y equals e to the negative 2x squared, y equals 0, x equals 0, and x equals 1 about the y-axis. Alright, so here's what we have. When we input 0 into this function, we get e to the 0, which is 1. The negative exponent means that we're going to have some kind of decay. So x equals 0 is this axis, y equals 0 is the x-axis, x equals 1 right there. We're spinning this region about the y-axis. So here is a general slice. So the radius, distance from my axis of rotation out to my slice, is x. The height of my slice is given by the function e to the negative 2x squared. So the volume can be found by integrating from 0 to 1. Circumference, which will be 2 pi x. Height, e to the negative 2x squared. Thickness, which is dx. To evaluate this integral, you're going to have to use a u substitution. You let u equal negative 2x squared. The details are worked out on your notes, and you end up with pi over 2 multiplied by 1 minus 1 over e squared. See if you can get that on your own. Next, suppose we have rotation about the x-axis. So I have the curve x equals 1 plus y squared. So a parabola, a sideways parabola shifted to the right 1. X equals 0, which is the y-axis. Y equals 1, and y equals 2. And I'm rotating this region about the x-axis. So here is my general slice. Now in this case, the radius is the distance from the axis of rotation out to your slice. That's given by y. The height of my slice is given by 1 plus y squared. So the volume can be found by computing the integral from 1 to 2, that adds up all your slices, 2 pi y multiplied by the height, 1 plus y squared, thickness dy. And that's 2 pi times the integral from 1 to 2, y plus y cubed dy, which ends up as 21 pi over 2. Next, let's consider what happens when the axis of rotation is not the x or y axis. So suppose we have the region bounded by the curves y equals x squared and y equals 2 minus x squared. So there's y equals x squared. Here is 2 minus x squared. And x equals negative 1 is right there. Okay, so we slice parallel to the axis of rotation. So there we go. There's a random slice. Now the difference here will be in the radius. The radius is equal to the distance from my axis of rotation out to my curve. So the distance from here to here is 1. From there to there is x. So there to there is 1. There to there is x. So that will be 1 plus x. And that even works if x is negative, because, suppose x was negative 1/2 and you were right there. The distance from your axis of rotation out to that point is 1/2. 1 plus negative 1/2 makes 1/2. Now the height is given by the upper curve minus the lower curve. The upper curve is 2 minus x squared. The lower curve is x squared. So h will equal 2 minus 2x squared. And thus the volume is given by an integral from, well, your slices begin at x equals negative 1, they end at x equals 1, 2 pi r, so 2 pi times 1 plus x, times the height, which is 2 minus 2x squared, times the thickness, which is dx. Now you must, when you compute this integral, those must be multiplied together. Don't go making up rules for integration. And you also can factor out a 2 from that second binomial, and that will give you 4 pi times the integral from negative 1 to 1, 1 plus x, times 1 minus x squared dx. When you work on all the details, you should end up with 16 pi over 3. In the next section, we found the length of a curve. So suppose we have a curve between A and B, defined by a function y equals f of x. We learned that the length of such a curve is given by the integral from A to B, the square root 1 plus f prime of x squared dx. And we also learned that if we take that same line and rotate it about, let's say, the x-axis, that's going to produce a surface, and that's the area of the surface area of the surface of revolution. And the way to find that surface area is the following. You integrate from A to B, and you think about it this way. We need to figure out the radius and the length. So the radius, the distance to a general slice, will be given by 2 pi f of x, that's the sort of circumference of a little slice, times the length, which is the root of 1 plus f prime of x squared dx. And so we'll be using both this formula in the next example and this one after that. So suppose we have the curve y equals 1 plus 6x to the 3 halves. We want to find the arc length between x equals 0 and x equals 1. So the formula for the length is we integrate from a to b root 1 plus f prime of x squared dx. So y prime is 6 times 3 halves x to the 1 half, or that is 9x to the 1 half. So the length of our particular curve is given by an integral from 0 to 1, square root 1 plus 9 root x squared dx, or the integral from 0 to 1 root 1 plus 81x dx. If you want to, you can use a u substitution and substitute for 1 plus 81x, or you can just sort of think about it as 1 plus 81x to the 1 half. That integrates to 1 plus 81x to the 3 halves times 2/3, and to compensate for the 81x, multiply by 1/81st. Evaluated from 0 to 1. Now that gives us 2 over 243 times 82 to the 3 halves minus 1. These problems often don't come out with very nice answers. If you get something really icky, don't be disturbed. Next, we'll find the area of the surface obtained when this curve is rotated about the x-axis. So for this, the formula for the surface area is the integral from a to b, 2 pi times y times the root of 1 plus y prime squared dx. So we need to figure out what y prime is. Y prime will equal 3 over 6 times x squared plus 1 half times negative 1 x to the negative second, or x squared over 2 minus 1 over 2x squared. And when you compute 1 plus y prime squared, you get x to the 4th over 4 plus 1 half plus 1 over 4x to the 4th. This is tricky, but this factors into x squared over 2 plus 1 over 2x squared, all squared. So for this particular region, the area is given by an integral from 1 half to 1, 2 pi times the original function, x cubed over 6 plus 1 over 2x times the square root of this, which is just going to root 2 x squared over 2 plus 1 over 2x squared. And from there, it's just really, really awfully tedious. You end up getting approximately 3.514. The answer is not pretty. So the important thing with that problem is you know how to set them up. Focus on the setup and just trust that the one that ends up on your exam will be one that's easy to work out. After volumes, areas, and surface areas, and lengths of curves, we moved on to applications to physics, and the first one of those was work. And work is found by taking the force times the distance. In the US system, the standard measurement for a force is measured in pounds. In the metric system, measure forces with newtons. So how much work is done in lifting a 20-pound weight 6 feet off the ground? So the work is found by taking the force times the distance. In this case, the force is 20 pounds. The distance is 6 feet. That's 120. And the units are, that has units pounds, this has units feet, given by foot-pounds. So 120 foot-pounds is how much work. A common example of variable force are springs. So we have a force of 100 newtons is required to hold a spring stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 20 centimeters? So here we use something called Hooke's law that says that the force acting on the spring is given by the equation kx, where x is the how far the spring is stretched from its natural length. So 15 centimeters is 5 centimeters past the natural length, or since this is in newtons, we have to have this in meters. So 5 centimeters is 0.05 meters. Now we know that the force required to move that spring, 0.05 meters, is 100 newtons, or 0.05 K is equal to 100, and that gives us a K value of 2,000. So my force equation for this particular spring is 2,000 X. And I will use that to compute. It says that the force required at any particular X is given by taking 2,000 times that X. So for stretching the spring from 15 centimeters to 20 centimeters, that's taking it from 0.05 meters past its natural length to 0.1 meters past its natural length. So the work is given by an integral from 0 to 0.05 to 0.1 of 2,000 x dx. And that differentiates to 1,000 x squared, 0.5 to 0.1, which works out to be 7.5 joules of work. And the last example we will do for work is lifting up a rope. So we have a heavy rope that is 50 feet long, it weighs 25 pounds, and it's hanging off the edge of a 100-foot building. So there's 50 feet of rope, it's 25 feet long. Now let's figure out how much it weighs per foot. So we have 25 total pounds per 50 feet. So it's 1/2 a pound per foot. Now we slice the rope into little pieces, common technique in calculus. We're going to compute the work to lift up that little slice. So it's the force times the distance. So that distance down, we call that x sub I. Now the force on that slice is the pounds. We have it's 1/2 a pound per foot. If the width of my slice is delta x, is delta x feet. So the force is given by 1/2 delta x. And from the total work, we add those all up, take a limit as n goes to infinity, we end up with an integral of 1/2 x dx. And because the rope is 50 feet long, we're pulling up all of it, we'll integrate from 0 to 50. And that's pretty easy. You guys can all do that. In the end, you should end up with 625, and the units are foot-pounds. Now the next thing we computed were moments, centers of mass, and centroids. So a centroid, remember that was if you have a region bounded by some curves, it had uniform density. The centroid was the balancing point of that region, or the sort of center of it. And it has coordinates x bar, y bar. So x bar is given by 1 over a, where a is the area of the region, times the integral from a to b of x times f of x minus g of x dx. And y bar is given by 1 over a, integral from a to b, 1/2 times f of x squared minus g of x squared dx. And this is called the moment about the x-axis. This expression is the moment about the y-axis. So find the centroid of the region bounded by y equals root x and y equals x squared. So first let's sketch that region. Here's y equals root x. Here's y equals x squared. Now to find the centroid, we must first find the area between those curves, and that is given by the integral from 0 to 1 of, now my upper curve is root x, my lower curve is x squared dx, and that works out to be 1/3. Now to find x bar, we will take 1 over the area times the integral from a to b, x times f of x minus g of x dx. Now 1 over 1/3 is going to give us 3. We have the integral from 0 to 1 of x times root x minus x squared dx, and that works out to be 9/20. Now y bar, the formula for that will be 1 over a, integral a to b, 1/2 times f of x squared minus g of x squared dx. So once again, 1 over a will be 3. We have the integral from 0 to 1. Actually, we can even say 3 over 2. And f of x is root x squared minus x squared squared dx, which, after lots of arithmetic, you also end up with 9/20. The final application to physics that we discussed was fluid pressure and fluid force. Now in this case we had some kind of shape. We wanted to compute the force of some kind of liquid on that shape. So suppose that this is a water level and our shape is submerged underwater. Now how to do that was this. We found the force by taking the weight density of whatever liquid we have, and we integrate from some y equals c to y equals d. And what we have to do is find the depth at that particular slice. So the depth we'll say is h of y. So h of y is equal to the depth multiplied by the length of the slice, dy. So find the hydrostatic force on one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. So we're going to assume we have this drum with radius 10. I'm going to put the drum at the origin. It makes it a little bit easier to do the problem. So the equation of that drum is x squared plus y squared equals 9. Now, because the drum is in water 10 feet deep, it's kind of like, that's the bottom. So this is 3, this is 3, which means the water level is up there, up at y equals 7. So for any particular y, the depth at that y is given by 7 minus y. So say you were at y equals 0. That corresponds to a depth of 7. 7 minus 0 makes 7. If you were at y equals -3, way at the bottom of the tank, 7 minus -3 makes 10, depth of -10. Next we need to find the length of a slice, so the distance from here to here, or here to here. And to use that, you take the fact that the equation of the circle is x squared plus y squared equals 9, which when you solve for x gives you x equals the root of 9 minus y squared. So your length is given by twice the root 9 minus y squared. So the force is found by taking the weight density of water, which is 62.4, times the integral from -3 to 3, the depth, which is 7 minus y, multiplied by the length of the slice, which is 2 root 9 minus y squared dy. And to figure this out, we'll break it into two integrals. We have 62.4 times the integral from -3 to 3 of 14 roots of 9 minus y squared dy, minus 62.4 integral -3 to 3 y root 9 minus y squared dy. Because of symmetry, this second integral is 0. So all we have is 62.4. So 62.4 times 14 gives us 873.6 times the integral from -3 to 3 of root 9 minus y squared dy. Now this, you notice, is a semicircle of radius 3, so we will have 873.6 times pi over 2 times r squared, which is 9, and that's about equal to 12,350 pounds.